So my name is Jim, and I'm the CEO of a company called Hopsworks, and we build a platform called Hopsworks. And Hopsworks is an open source platform for the development and operation of AI applications at scale, and it includes the industry's first and most advanced feature store for machine learning. And today I'm going to talk more about the Python-centric nature of our feature store, so how you can use Python primarily to interact with the feature store. So to store your features, use your features, and we'll go a little bit further and show how we can do real-time machine learning with the platform as well. So I'm going to start by just some level setting with a lot of people about what do I mean by a feature store, what do I mean by a model, what do I mean by production machine learning. And I'll start at machine learning and what is a productionized model, because I hear this term quite a lot. And I don't use the term productionized model, I use the term prediction service. And a prediction service, I'll use the analogy of a bus. So if I go and train a model and I use it to make some predictions, it's all very nice. It's almost like having a bus that brings people on a one-way trip, which is very nice, but that's not the same as building a bus service. So a bus service, as you know, would need to have a timetable, a route, it will need to have drivers, it will need to have maintenance, it will need the buses. So a model that you want to make available as a prediction service, whether that prediction service is a real-time prediction service or whether it's a batch prediction service, so it's going to run on a schedule, so periodically you can generate predictions once an hour or once a day. Either way, you still need to put together the infrastructure to take your data, turn the data into features, and then train models with those features. Then deploy your model, make it available for either the batch or operational services to use, and then you're going to have to make your predictions, and you're going to have to then build all of this together as an infrastructure. So the kind of things you need to do are, you need to support automated training and testing and deployment. The system that you build, ideally, it will also be highly available. So if there's a partial failure somewhere, the system should continue to running. It's a prediction service. It should continue running if there's one component that's failed. It should be scalable. If you get a lot of traffic on this service, you'd like it to be able to handle that increased traffic. And in particular, I'm going to talk about this issue of the feature store. So if your model, that your prediction service is a real-time prediction service, we're going to use the feature store to be able to retrieve these features and add them to our prediction vectors or feature vectors to give us richer predictions with which our prediction service can give better interaction with the users. So warning, that's a bit of an analogy. So I'm going to jump in a little bit to how does a business add value with not just batch, but also operational AI. So typically what we see with companies we work with is that if you don't have your data house in order, well, really getting into AI is maybe a bit premature. So it's probably a good idea as a company, if you're an enterprise that has a certain amount of tabular data, so data in tables in a data warehouse or in a data lake, but you're also starting to do BI, business intelligence on it, to understand your business. So that's the point at which many organizations will engage in what we call laptop ML. And laptop ML is really the idea that you can take some of your existing data and you might have a hypothesis about a prediction service you can build with your existing data. So you train a model on your laptop to see if it works, and if you're happy with it, you might then move on to the right-hand side of our diagram here, where we call predictive and prescriptive analytics, where the first step many organizations make is to do what we call batch machine learning. So being able to make predictions, but on a schedule. So once a day, once a week, once an hour, you have a system that's going to read some new data, it's going to make predictions with the data, and it's going to use those predictions to add value to your business. Whether that could be optimizing something or reducing costs. The basic idea is that you come up with the prediction service idea, and then it's delivered as a service that runs periodically. Now, higher business value you'll see, particularly in consumer related areas, of real-time predictions. And real-time predictions can be anything from, you may be familiar with YouTube, I'm sure many of you are, and it'll give you predictions, but the predictions will be based on maybe what you looked at yesterday, or maybe the trends over a period of time. It's historical data, and that's great, and that works very well, but my kids prefer TikTok, which gives you real-time predictions using the very latest data. So what have you looked at in the last 10 seconds? That will influence what it's going to recommend in the next few seconds. And we see this and I'll give an example later on of network intrusion detection. So if I have an AI, a model trying to predict if network traffic is potentially intruding into a network or not, we need the very latest data or features about that attack. So we need to know how many IP packets are coming from a certain address over a period of time in order to make a very timely but also accurate prediction about whether intrusion is happening or not. So there are many problems at the top that can add a lot of business value, but there's also many problems in terms of batch machine learning and even real-time predictions with historical data. Now, so now that we've cleared up some of the ideas about prediction services, what value they can add to your business, I'm going to talk a little bit about machine learning operations, or ML ops. It comes from the world of DevOps. And the reason why I do it is because before I introduce the feature store, I'd like to just tell you the feature store is part of a larger infrastructure you need to go from raw data to these prediction services. So if we start in the at our enterprise data in the middle at the top, you can see that we will need to take that enterprise data and transform it into features. So we have feature pipelines that enable us to do that. These are programs which can aggregate data in your enterprise data warehouse or data lake or databases and write those features to the feature store. And those features are the compressed signals that you're going to use to train models. So the feature store we'll see has something called an offline, a feature view offline API to create training data. You'll need then to train models. And today we're going to talk about Python for training models and Python for interacting with the feature store. So using Python to write the features in the feature pipeline, but also retrieving features for training data with the offline API. And then when we have models that we deploy that we want to use in either a batch service or in an operational or 24/7 service, we'll need to manage those models somewhere. Typically, organizations have something called a model registry or model repository. And if your models are being served because they're running 24/7, they're operational models, they can also plug into the feature store via this online API to retrieve features at very low latency. So what that means is if I have a model, for example, doing network intrusion detection, what I can do is my service out here, which is trying to predict if the traffic from a particular IP address is potentially intruding in my network, it can use that IP address to look up in the feature store recent historical information about that particular IP address. So how many packets have arrived in the last 5 seconds? Do I trust this IP address? Is it on a VPN that I'm familiar with? And so on. So we can so that the operational service that's trying to predict IP intrusion detection doesn't need to maintain all of this historical data. It can go to the feature store via this online API to get it. So the operational and batch services that are making predictions using the models will also generate logs. They're going to make predictions, and at some point you may be able to figure out the outcome of a prediction. And that's really valuable because then you get new training data which you can make better models with. And with better models, you'll be able to get better operational services and better batch services, which hopefully will attract more users, which will in turn generate more data. So this is often called the machine learning or AI flywheel, that if you get it going and you get more data coming in and better services and more data, then you get this positive feedback process in place. But you need to put the infrastructure in place. I'm going to talk primarily about the feature store, but I'll do some demonstrations of model serving, in particular on our platform with Kubeflow model serving or Kserve, and how that integrates with the feature store. Okay, so let's have a look at what is a feature store for machine learning. And if we look at the top of this diagram, what we can see is that we have a case where there's no feature store. So we have our enterprise data in the top left-hand corner and a data engineer who has access to that enterprise data, but the poor data scientist in the middle doesn't have direct access to the enterprise data. And that's quite a common scenario at many organizations and enterprises. the data scientist has to request a dump of data from the data engineer, who maybe is going to go to BigQuery or Redshift or Snowflake or Databricks, get some data, give it to the data scientist who will train a model. And then when they're finished training a model, they'll hand it over this wall to an operations person, often called a machine learning engineer, whose job it is to host these models, make them available for the batch and operational services that are going to use them. So really operating all of the infrastructure. Now, if the model that you trained needs to go back and find out for operational data, well, you know, I got this IP address and I need to know how many packets have arrived from it in the last, 10 seconds. Well, then you need to go back. The model needs this operational data, needs to go back to the enterprise data to figure out that. That's where we get all the problems. This handing the data over walls, models over walls, and the lack of collaboration between the teams. So the feature store is a collaboration tool, platform for bringing together all of the data for AI from the enterprise data on the left to the model serving on the right, and providing APIs to allow the data engineer, the ML engineer, and data scientists collaborate. Now, we provide a little bit more. I'll talk about later this notion of projects as a way of collaborating. But we can say basically that this platform is a data platform for bringing together all of the data in your organization for AI and making that data available to the models that are running 24/7 to make predictions with. Now, that's the feature store at a kind of a collaborative architectural perspective, but how do I get data into it? And I alluded to this in the MLOps slide. We have a pipeline, a feature engineering program that's going to write data to the feature store, and there probably will be more than one. So when you have many different data sources for your features, and those data sources are being updated at different cadences, so maybe one is updated every hour, one is updated every 10 seconds, and one's updated every day, you probably have a different pipeline or different program to read that data, that new data, turn it into features, so compute aggregations or potentially transformations, and write it to the feature store. So we'll look a bit at doing that in Python today. Now, in our case of the feature store, we write to tables that we call feature groups. So the feature pipelines will write to these tables, and then we'll have reusable features. The features can be used in many different models. And the way that you read data from these feature groups is via what we call a feature view. And we can see here that the black arrow indicates that we have online models or operational models that need to read real-time features from the feature store. And then we have the model training or training data, and then the batch inference programs that need to read batches of data. So these are the two main APIs to the feature store for reading. One is low latency real-time, and the other is high throughput batch data. And we'll see that they're unified in what we call a feature view in our platform. So how do we write these feature pipelines? I said we would concentrate on Python today, but you can of course use other technologies. So people do use SQL for computing aggregates. Spark is quite popular, PySpark, Spark Streaming, and Flink is popular for real-time feature engineering. So the kind of steps that you perform in feature engineering are that obviously you have to extract the data that you need to process, you compute aggregates on it, we validate the data typically, and then at some point we're going to transform this data into the numerical format that the model expects. So in our platform, the open source Hopsworks platform, we support Python and Pandas as a way to write data to the feature store. You can compute your features in a Pandas data frame and write that, or in Spark data frames or Spark streaming data frames, or in Flink. And then this way we're going to write data which will be stored inside the Hopsworks feature store. Now, there are many cases where people have their data on an existing data warehouse or data lake or database, and they already have features there. So you might have a pipeline to compute aggregates of orders from customers by day or by hour, and it's done in Snowflake, and you want to use those as features. Well, there's something called connectors in Hopsworks that you can use to mount that table in Snowflake into the feature store as a set of features that can be used for batch and training. So we're not going to cover it too much today, but it's interesting to know that that capability exists. So your training data and your batch data doesn't necessarily need to be stored inside the platform, but it can still be reused with other feature groups or tables that may be stored in the platform. So you can have a mix of data stored inside the platform and outside the platform. So I mentioned that we write to the feature store with feature pipelines, but the abstraction we use for that are what we call feature groups. These are tables of features. And then when we read from the feature store, we have something called a feature view. And a feature view is basically a set of features that you select from the different feature groups. And you basically say, these are the features I'm going to use in a model. So you can think of the feature view as being the representation of features you want to use in a model. So when you have a model, your model will need to you'll need to train your model. So you'll need to get training data for the model. So that's where we use this offline API. So we say that I'm creating a feature view. These are the features I want. Maybe I'd like to have the product features. I want to have the order features and the user features, and I'll join those features together, and then I'll get a feature view. So feature view is a logical grouping of those. It's only when we want to create training data that we actually need to go and read the data from the different feature groups. And some of those feature groups will be inside Hopsworks. If you have connectors to external databases, maybe it'll read the data from those ones, but the platform will join all of the features together and enable you then to retrieve that data as training data for your model. And then also for the online applications, they'll use this online feature view API to retrieve feature vectors. So just a row of features, because that's all you need to make a prediction for individual prediction request that comes from a client. So we're going to look at Python and how we write to the feature store in Python. And this is a very simple example. We can see here that there's a library called HSFS. So you'll need to pip install HSFS. And you can do that in any Python 3.7, 3.8 environment. You can run this code on your laptop. The only thing that you'll need to do is you'll need to know the host where your code is running. And there's a project that you're going to connect to. So you can have many projects inside the platform, and each one has its own feature store. So you can think of a project as being the name of a feature store. And then you'll need to have an API key that you can create in the platform we'll look at later, that's going to authenticate you and also authorize you that you're allowed to access this particular feature store called orders. So with this connection object, we can create a feature store object. And in this case, we're going to write features in a pandas data frame. So this particular pandas data frame is taking data from a CSV file. We're going to remove some of the columns. And this is now a pandas data frame called prices. And with this prices data frame, I can actually insert it. So the last line is saying prices underscore FG, the prices feature group. I'm going to insert this data frame into it. But first I have to create the feature group. So this feature group I'm creating with a name. You can see we have versions associated with the feature groups. I'll get to in a minute. But then if the feature group is available both in the online API and the offline API, which is set here, then we have to set the primary key. Now, by default, you will probably nearly always need to have a primary key for your feature groups, because if you want to ensure that there's no duplicate data, for example, in rows, then you'll need a primary key specified here for your feature groups. So here you can see the primary key is the order ID and the order item ID. So we're interested in the order prices for this data. So this will get the features into our feature store, and what will happen is that it'll write a table. We've got this table called order prices, and it was version number 1. And every time we write to this feature group, we'll actually get a new commit and timestamp. So the data is written atomically to this feature group, and what we can see is happening here is this is my feature pipeline. So the feature pipeline, the feature group is already created. It's going to read up some new data in the CSV file, get a reference to the feature group, and insert that new data. This will do what we call an upsert. So it'll either append the new rows, or it'll update existing rows. And you can see it will add a new commit to the feature group. Now, this is what we call data versioning, because you are in fact able to go back in time to look at earlier versions of your data. But the more common thing and more important thing, I think, related to managing your feature groups is managing the versions of the schema of these tables or feature groups. So it may be the case that you want to try a new set of features, because you say, well, you know, I've got some new information about the customer related to the online store, and I'm going to use that data in my order prices feature group. So what I need to do is create a new feature group here called order prices version equals 2, and I've added some new data into it. So we do need to backfill this feature group because it will be a new table. There won't be data in it to begin with. It's a new version of the feature group. We can copy the data from the existing feature group. If we're just appending new columns and we specify a default value for that new column or new feature, well, then we don't need to create a new version because it's not a breaking schema change. But if you do need to change the implementation of a column, maybe you have an embedding and you have a new algorithm for computing the embeddings, or maybe you're removing a column, well, then you have to increment the schema version. So this version equals 2. Okay. So we have versioning, which is great, and let's go and let's move on to the next one. So what else do we need to make sure when we're developing these particular feature groups? So we also need to ensure that the data that we write is of good quality. Okay, so if we write garbage in and we train models and we make predictions with it, we'll have problems. So typically, data validation frameworks are quite popular. So TensorFlow data validation, Great Expectations, DQ are some of the frameworks out there that are widely used in machine learning. So for Python, Great Expectations is become one of the de facto standards for validating data. So what you can do in our platform with HSFS is you can write data to your feature group, and transparently you can associate or attach what we call expectations for those features. So maybe we're going to say that this feature value will lie in a particular range, or we can say that there shouldn't be any missing data in this particular data frame that I'm writing. So this column shouldn't have any missing values. We can also take data that we write and profile it to get some expectations. So you can profile it to say, well, the minimum value is this, the maximum value is this, standard deviation was this, and the mean value is this. And when we write the data, we want to find out about the quality of the data that's written. So we can get what we call feature quality reports that we'll display in the UI, and also metrics, so measurements or statistics over the features. So those metrics are computed in pandas, in the pandas data frames that you write. So in the UI, it kind of looks something like this. You know, you define your expectations, and that you define the columns or features they're associated with in the feature groups. And as the data is written, you can see if they succeed or don't succeed. But the code, it looks at something like this. And this is really mostly Great Expectations code, but I'll highlight the parts that are specific to the feature store. So firstly, we want to create a validation store for where we're going to store these expectations. So we do that on the first line. And then we get a reference to our feature group order prices. So what we're going to do is have some expectations. In Great Expectations, we have something called a suite, an expectation suite. That's a set of expectations that I want to apply in the data, in a data frame. In this case, we're only adding one expectation. So in the expectation suite, we're adding an expectation where we expect the column max to be between the values 1 and 20. So if we, and this is for the column number of order items. So if this order coming in, if it has a number of order items lower than 1 or higher than 20, then we'll have an error. So we can see here that we say we're going to save this particular expectation suite with the feature group. So now we're associating with the feature group, and we're going to make sure that this ingestion policy will always be executed. We're going to run the validation. It'll be true every time, because sometimes when you're developing, you don't want to necessarily validate all the data because you're in debug mode, and it does make things go a little bit slower. So you can turn it off when you're in development, but when you're in production, then you'll turn it back on. So when you in your feature pipeline, when you just read up new data into a data frame, a pandas data frame, and insert into your feature group, all the expectations you've defined on that feature group will get run in the background, which is very nice. So this code becomes very clean for your feature pipelines. You just need to set up your expectations. Typically, you'll do that in a separate program. And you can do things like, if you're in a notebook environment, you can just get your validation reports for a feature group or get the latest one, and you can see them in your notebook. That you don't have to go back to the UI of the feature store to find out how things are working. So this is really just here for completeness because we're supposed to talk about the Python feature store today, but often if you want to have real-time features, so you want to have features which are very fresh, so maybe only 10 seconds, 30 seconds old, Python programs, there's a couple of frameworks out there, but nothing we currently officially support, but that may change. There's one called Bytewax, which is quite nice. But right now, most people are running PySpark or Flink to do real-time feature engineering. So this is just an example to show you some code for how it works. We're reading data from Kafka, computing a 10-minute window on it, and writing to the feature store. But we'll skip over that for this talk. So that covers writing to the feature store. So when we've written to these feature groups, we want to use those features to train models and to serve features to models. So the feature view itself, when we define one, we're going to basically say the following. You see this line up here at the top. Select features from feature groups, and we just select the features. We've got product ID, the category name for the product, the number sold in the previous week, the amount of sales that we made in terms of money, and that's basically defining the feature view for us. Now, when we want to create training data from the feature view, we'll need to say which column or specify a column that's going to be the label, because we're assuming here supervised machine learning. Other things that we might want to do is we might want to say for the training data, well, I'm only allowed to train this model on a particular type of product, perfume, so I'm going to do that. But maybe you're restricted by geographical regions, so you say I only want to create training data for people based in North America, for example. The particular features that we have in our feature groups, often we store them untransformed in the feature store. And what I mean by untransformed, if you're familiar with machine learning, you'll know that if you have a numerical feature like a person's age or the price of a product, often we'll normalize that, meaning we'll squash it into a range between 0 and 1, because that improves the convergence properties of our machine learning algorithms. And maybe with categorical variables, we'll turn them from a string format into a numerical format. But these transformations often happen after the feature groups. And in our platform, you can define transformations when you're creating training data. So you can say, I'd like to transform this column with this transformation function. And we'd like to split the training data into train, validation, and test sets. And then finally, how do I want this trained data? Would I like to receive it as a pandas data frame, or is it too big to be retrieved as a pandas data frame in memory? I prefer it as files, so CSV, Parquet, or TF records, TensorFlow record files. And this will be then my training data, the product sales. But it also be, we'll see the feature view is also used to retrieve the feature vectors at runtime. Now, one of the things that feature views do when creating training data, which is very important, is they do something called a point-in-time correct join. Now, this example is going to show you, we can see here, we're creating this feature view called weekly product sales, and we're creating it from some features in order item weekly and some in product. And we can see on the product ID, we've got an event timestamp, but there's no event timestamp over here in product. So I don't have to worry in this case about making sure what was the category of this product 12 when the sales were, at this particular event timestamp 1000. So what we get back is we'll get back our product ID, the sales, the number sold the previous week, the category time photos, and so on. So we're not too worried about the event timestamp because we know that the value of this product was true for all time. If, however, we did care about that timestamp, then the feature store will ensure that the timestamps match up, that we don't get what we call a pollution of the data set, right? So we don't get references to the product category name that were in the future. so that when we had the sales at that amount, that was the exact name of the product category at that point in time. So let's look at how we create a feature view in the platform. So in that case, we had two tables. We had the product feature group table or feature group, and we had the order item weekly feature group. So if you want to join features together from the different feature groups, you basically select features from it. So in this case, I'm selecting all of them. Now, I can select just the names of features. So I could say, hey, I don't want all of the features. I just want to select the sales and the sold previous week from order item weekly. I'd like to select just the category name, not photos quantity in the product. But in this case, we made it easy for ourselves and just said select all of them. So then you join those features with the other features that you're interested in from other feature groups. And we'll get back this query object, which is contains a logic about how to do this point in time join between the feature groups. So the feature view is basically the set of features contained in this query object, because when we create the feature group, we say, here's the query object that we use to create the feature group view. And then we can add some metadata to it. We can say the name of the feature view, the version of it, the description, the label at this point in time. And then what we can do is we can get training data from this feature view. We can basically say, you know, please get me all the training data that's available for this particular feature view, and I get it as a pandas data frame. So I can go ahead and train a model with that. I might also want to use this feature view because my model is running online. If my model is running online, I want to use the same feature view to basically say, hey, I want the latest value of the product sales, and here's the ID for the product. So we pass in the ID, it's 1, 2, 3, 4, and I'll get the latest sales weekly features. And this row of features I can then use to build my feature vector to make my prediction with my online model. So we can see here that these two ways of using the feature view, one to create training data and one to get a row of features, are quite different. This one is a high throughput operation. It's going to get a lot of data, a lot of historical data, and do this complex point in time join. And the get feature vector is going to basically do the primary key lookups on the different feature groups or tables that contain these features and join them together for me in the correct order, and ensure that they're the correct types of the features when I get them back. In this case, we get them back as a Python array in HSFS, and then I can build my feature vector with that. So there are pre-engineered features. So I mentioned point in time correct joins, and I said the previous example didn't have a timestamp for the product because that timestamp already existed. So let's look at an example where there is actually a event time for both of our feature groups. So we can see here on the left we have seller ID 1112 and the same seller over on the right hand side. So we're going to join these rows based on seller ID. But what we want to do is find out the average review score for the product at a particular point in time. So on October the 22nd, the delivery time for the product was 72 hours, but the review score was 3.8. However, in December, the delivery time increased to 88, and we can see that the review score decreased to 2.8. So if, for example, we want to also create training data with the November row, we have to decide, do we use the 3.4 average review score or the 2.8? Well, in this case, we know that we have to use the 3.4 review score because there was no review score in November. So we used the most recent one, which was in October. We can't use the one in the future. That would be data leakage. So our feature view will say these are the features that make up our the features that we can use to create training data with and feature vectors with. And then we can, with that feature view, we can create training data. We say, okay, I'd like to create CSV training data. And we can see that it creates 3 rows. Even though we only have 2 rows in the seller's review quarterly, we can infer the average review score in November because it was the most recent one. And this is what the feature store will do for you. It'll create this data correctly for you. This point in time join will be executed correctly for you. You won't have to know the complex logic required to run that particular query. We just have the simple Python API call we saw earlier. Now, feature views also can include what we call transformation functions. So and I showed that earlier, when we retrieve the feature, we say, I want to create training data with these features. I'd like to maybe transform this is UP, the user profile, or the transactions T. If I apply transformation functions such as normalizing a numerical feature, I want to make sure that that normalization is done both when I create the training data, but also when I serve those features to a model running in real time. So when I retrieve the feature vector from the feature store, I want to retrieve the data transformed. I don't want to retrieve it untransformed. So what we can do is with the feature view, if we specify transformations on individual features, the API or library will apply the transformation functions for you, both in serving and when it's creating training data, and ensure that the same code is run in both cases. And that code, that transformation function also requires state. It requires the state of the training data in particular. So, if I'm normalizing, I only want to normalize based on the train split, not on the test split. And then when I'm normalizing in runtime, I want to normalize also based on the train split, the value of that feature, the average value of that feature in the train split, not in the all of the data and not in the test data for sure. So, what else can I do with the feature store? I can create incremental training data as well with feature views. The feature view has a set of features, but the data behind those features in the feature groups has a starting point and an end time. So if I say get training data and I don't specify the start time or the end time, it will give me all the available training data. But it may be the case that I created training data V1 here, and this was October the 1st, but then we came to the end of December and there's way more training data available in the different feature groups. More data has been written to the platform. So I create training data V2, and I can create it from the beginning of time of the feature view to the current time, which is great. But then I decide, okay, hang on, this is going to be quite expensive if I have to recreate the training data every time and retrain my model on all of the training data. Maybe I should do some incremental training of my model. Maybe I don't need to run over many epochs, just a single epoch. I can save my model after I've trained it, and then I can reload that model and run it on the new data that arrives. So you can do that with the feature store API, feature view API quite easily by saying get training data on the start time and the end time that you want. So what if I want to save the training data from a feature view to file because it's too big to store in memory? I don't want the pandas data frame back. It's going to be many tens or hundreds of gigabytes. Well, you can call featureview.create training data set. And in this example, I'm also adding in a transformation function that I talked about. So I'm going to take the feature called price, or column called price, and I'm going to apply this normalized transformation function to it. You can see I defined the normalized transformation function up here on line 2. It's a min-max scalar transformer. And you can define and write your own transformation functions. And in this case, we're going to store the data as TF record file format. We're going to store it to a bucket in S3 because maybe I'm training my model, in a notebook running on AWS. I just need access to the bucket to read that training data, to train my model. And you can also define how you want to split your data. You can do a random split, and then what type of splits you want as well. So once you've created your training data, you can train a model, and this is standard, TensorFlow, PyTorch, scikit-learn code. Nothing you need to do here. The only thing I've added here is our platform does have a model registry. So if you save your model in TensorFlow, we save it to a path called export path. We can actually just register that model in our model registry by calling HSFS save model. It's actually HSML, but so yeah, and then you can pass in metrics. If you've computed metrics in your model, it'll be stored in the platform with your model. And we saw some of this already, but just to show you again, when I want to use this model to serve feature vectors, well, what I need is the ID. So when I created my feature view, the different feature groups had primary keys. And when I joined them together, I probably joined them together on some primary key, which is now become the primary key to my feature view. You can, of course, inspect the object to see what your primary keys are. But in this case, we've got a single primary key, product ID. And with when we want to make a prediction for in this case, for an individual product, maybe it's the most recent sales on it, we go to the feature store to get back the pre-computed features on recent sales. And that's going to be in this ordered feature vector. And with this, which is a Python array with the features in the correct types and the correct order, we can just call model.predict if all the features come in here from the feature store. And then that's our prediction that we can return back to the application. So I'm going to run briefly through some of the properties of the platform. That's the code covered and the APIs. The most important APIs, but our platform has some, as it's a data platform, it's like a database. You care about throughput, availability, and latency. So we care about how fast we can write, the uptime of our system, and the response time of the system. What's unique to feature stores is we also care about how old the features are. If they're going to be from yesterday or from an hour ago or 10 minutes ago, we care about that. It's feature freshness. So for example, availability is important. We know this large retailer in Europe who were using an embedded in-memory database as their feature store. It crashed on Black Friday, and it wasn't highly available, so they lost revenue. We also worked with a bank who were using Pandas and Python, but needed to onboard a new use case for their fraud model, which is a huge amount of data. So we had to switch from Pandas to PySpark, which is pretty straightforward in the platform. We also know a telco company who are doing network intrusion detection. And they were doing it with Spark Streaming, which gives you relatively fresh features, maybe 20, 30 seconds. And you can improve the freshness by going to Flink, which is a real streaming API, not batch-based. And that improves then the main prediction problem or prediction service, which is network intrusion, and improves the network intrusion detection rate. And then finally, we worked a bit with a music company nearby, and they are testing a real-time recommendation service that needs to look up 250 candidates from the feature store for ranking them in the ranking and retrieval infrastructure. And they needed 250 candidates in less than 30 milliseconds. So our feature store manages that. So if you look at it as a whole, when you're writing feature pipelines, if you get to more than 100 gigabytes of data, you might need to move off Python. If you're getting more than 1,000 requests per second, you might need to consider our feature store could be scaled out or scaled up, and we can handle millions of requests per second. If you're creating more than hundreds of gigabytes of data per second, you might need to go to files rather than Pandas data frames for throughput. If you need very low latency in your feature store, our feature store is an in-memory feature store, so you can get less than 1 millisecond latencies, but P99s on single millisecond latency throughput. And then you need to care about availability potentially. So if your feature store is going to power your online operational models, you may need very high uptime support. So the main database behind our feature store, RonDB, is used in production in services that require 5 nines availability. And then finally, if you need really fresh features, you may need to look at streaming engines such as Flink or PySpark. So a couple of other points about the platform. Hopsworks is a feature store. It's open source. You can go ahead and try it. You can go to Hopsworks AI and sign up, and it's running in the cloud. But it does have a few more things about it. So you can manage your teams in Hopsworks. It can manage data for AI. It's good performance we saw already, and we can deploy it in any cloud or even on-prem. So you can manage teams inside different projects and have feature stores private to those projects. A project is a place where we bring together all of the different actors from data scientists to data engineers to business analysts and machine learning engineers, that they can work together to put models in production. And we saw already that the main abstractions inside the feature store are the feature groups that we write to, and they can be have online features or offline features. They can also come from outside the platform, external feature groups. And the feature views are the way in which we can create training data or batch data, but also get live feature vectors to models. The platform does enable sharing between these projects, which are this scope, privacy scope. So a project is also a sandbox in which you have data and members, but you can share data across projects securely as well. So let me show you a demo. I have a few more minutes, so I'm going to show a little bit of the platform, and we'll show how to use it from Python. If you're curious and go to manage.hopsworks.ai, you can register for an account and create a cluster. I think you'll get a demo cluster straight off the bat. The platform, as I said, is clusters, but they're dynamic. You can add and remove workers. You can make them auto-scalable. You can stop them when you're not using them. You can create backups of them, and so on. But I'll just show you one that we're running here. So you can see in this example, I think I have a bunch of projects in here. If you run the demo tour, if you use the demo project when you try out the platform in manage.hopsworks.ai, you'll run this project. It'll create this project for you. So this project actually, what it does is it runs a job. In this case, it's actually a Spark job, but it will create a bunch of feature groups and training data sets for you. So you can see a bunch of them that were pre-created here. I ran these ones just a couple of minutes ago, but the other ones are related to sport, and these ones are created already. So we can see if we just pick one of these feature groups, season scores features, and this one is also available online. And I can zoom in a little bit because maybe you won't be able to read all of that. You can see it's online true, it's cached. These are the features inside the feature group. So it's the team ID, the average position of the players, the sum of the position of the players, some provenance information, expectations, tags, and so on. We can get a preview of the data in here as well. So we can see some of the values here, and this came from the online feature store. It's a little bit quicker. When we wrote the data, it computed statistics by default. So when the job said, well, by default, we'll compute statistics on the feature groups. When they're written, we can see it wrote these histograms of feature values, but also wrote scripted statistics. So minimum, max, and mean, sum and standard deviation of this feature, average position, and also some more information about whether the feature is complete, there's missing values, whether they're unique, and so on. I'm not sure if I did it compute the correlation matrix computed over this. You can also see activity in the feature group, so when it was created, commits, and every time you write to it, you'll see more activity. So I actually have, I think this one I ran earlier, which is a bit more activity on it. It's called sales. You can see it created, okay, so I only created this one because actually this one is on version 3. So I mentioned already that we can have multiple versions for feature groups. So this one you can see here, it says it's version 3, but I can go back in time to look at version, not back in time. In this case, I'm just changing the schema version, and this is version 1. And there's slightly more features, I believe. And we can see the activity of version 1 was when it was just created. So the feature groups are these reusable sets of features, and we can search for them. And we can also create training data sets from them. And this is one of the training data sets. This one is called Tour Training Data Set. And we can see, if we look at the features inside it, you can see it looks like a feature group. But we can see that there's 3 features coming from 3 different feature groups, okay? And we get more data about the splits, you know, the query used to create it, the API, statistics, activity, and so on. And we can see here the feature values here. So, and remember that these statistics are going to be different to the feature groups because maybe the data used to create the training data is not all of the data in the feature group. It could be just over a period of time. And then finally we have connectors to allow you to connect your external, you know, you can connect anything from Redshift, Snowflake, Kafka, GCS, Google BigQuery, and so on. Okay, now I said I'd go through an example called intrusion detection, and I'm running out of time, so I'm going to go relatively briefly through this. So I actually created this feature group called IP 10 minutes aggregates. It's computing the 10-minute aggregate of IP address requests coming in from an external source. So I have some training data in here, or it's not training data, it's some raw data here. We have a look at it here. It's called sample click logs, and it's 4.3 megabytes, so it's not that big. And I did run a notebook. I think the notebook's still running here. It's this one here. In this case, you know, I basically created, you can see this is our data here. We've got an IB, an IT, and so on, and I wrote this data to the feature group. And then I trained a model in here. So in this model, you can see I'm reading the data as a CSV file in Pandas. It's a Python program. And then I'm getting the features that I need. In this case, we're just looking at that one feature, the number of packets per 10 minutes, and we train a model. and we deploy the model then on our platform. So we can have a look at that while we're here. So in this case, I'm going to change the profile to data science, where we'll see the model registry. So when I deployed the model, which was just, deploying the model was very straightforward. It was just this line of code here. You can see it's here. We created, this case, we said it's a TensorFlow model, and then we're just saving it, and we're using the normal TensorFlow export path where the model was saved. We also include the input schema for the model and output schema, and an example row, which is kind of nice, because then you can test the model. So let's go back and see here. So this is our model here. We can see there's only one version of it, but you can have multiple versions deployed to models. We can see the input schema, output schema. You know, we can see some code snippets for how to use that model. And if we look at the deployment, I think I should have a model running. So I deployed this model earlier. You can create it by, in this case, it's TensorFlow serving and it's Kserve. But you can have scikit-learn, of course, and you can have TensorFlow and PyTorch and so on. So let's look at this particular model. And it's deployed, and we got some metrics. The accuracy was 0.6, it's not very accurate. I want to look at the deployment of it, not the actual model. So let's click on the name of the model to get it. So this is our model here, and we can see that, you know, there are statistics in Grafana and Kibana, and it's running. It's Kserve, which is a Kubernetes model serving server, and it's running version 1 of the model. It says, I actually ran some experiments earlier, so we can maybe look at, there should be some metrics from earlier when there was some data coming in. Yeah, we can see some data from earlier. So, you know, we can see in here then, you know, you can see the latencies on this model. It was running from Colab, so the P99 was up at around 20 milliseconds on average, a little bit high, but it's running from Colab to another server running somewhere else. We can test our model by clicking run test, and this was the sample data that was pulled in. And I'm going to just show you how to use this from outside the platform. So, you know, this is a Python native feature store, so we can, in this case, I can connect to the feature store from outside. This is a Colab notebook for those who are not familiar with Colab. But you could run a Jupyter notebook or just a Python program in any Python environment. It could be SageMaker, or it could be a notebook at your office. And what you need to do is just connect to the IP address of your host. Now, in this case, I'm actually running the open source version, so I set hostname verification to false because I didn't set up in the managed platform. Of course, you get a certificate here, but I set that to be false. But you can create an API key very easily. You can just go into your accounts, create an API key here. You might want to, you know, just getting started, select all of the scopes, which is not obviously, you know, following the principle of least privilege, but you can copy then that API key and use it then to connect. And typically you should put that in a file. Here I put it in just in the notebook, and you don't see it here. But so let's have a look at how we can access the platform from outside. This is for model serving. Now we're just looking at the model registry, seeing what models are in there. And we can see there's one model called the IP intrusion detection model. And we are checking to see if it's running, and it's now running. We can see you can call start, and it will just say it's up, the deployment is already running. And now I'm just going to make a quick prediction and see what happens. So this is the input data for this prediction. In fact, you can see it here. Maybe we can zoom in a little bit, make it a bit bigger. So we can see that it made a prediction here. In this case, it's predicting the probability that we have intrusion from that given IP address. And in this case now, I've started actually quite a long cell I can see here, because it's going to run 1,000 predictions. So what it's doing is it's just calling predict with the data that we had earlier. And if we go back to our model deployment here, we'll be able to see that those predictions are being made on the, we'll be able to see it from Grafana, that these predictions start arriving in here. So we have some, you can see we have some charts showing the predictions arriving. We can see them arriving in here, and there's the latencies for them, and then the number of predictions per second. So I think I've run out of time. I've kind of covered an end-to-end example here. We've seen, you know, what capabilities are in the platform, how we can write our feature pipelines in Python, how we can create training data, how we can train models, and even use those models for model serving in the platform. If you want to learn more, you can go to hopsworks.ai, The easiest way to get started is probably with the managed platform, but you can also install the open source platform if you have a VM to get started there.